Okay, so continuing on with class 2, I'm going to try to, I spoke a lot in the first video for class 2 with a lot more detail than I meant to. So I'm going to go over this and the example together. Also introduce, this is going to be the normal stress video with some examples of normal stress. And then I'll make another one for shear stress, and I won't go into as much explanation of it. Okay, so here we go. Here is uniformly distributed stresses is how Shigley brings it out. This might not be the page number anymore, depending on what edition that you have. But we remember that we said this was F over A. Axial normal stress, right? Just F, and then there's your stress, and it's acting, and we're assuming that it's normally distributed across the entire cross section. Now, if you don't, normal stresses for beams, they're distributed linearly, right? They have, like, if this is the case that they have here, where they're showing, bending moments that are coming up here, right there, as they show them, that's going to be compression at the top and tension at the bottom, right there. So it's going to be all the way, and any of the points along here, any of the points along there. These are all going to be, and they're going to be slowly smaller and smaller till you get to the neutral axis, right? That neutral axis or centroidal axis where it's 0. So if you were going to generally say this right here, let me see. I got to make sure that where did my oh, there it is right there. Just want to take a look at my notes that I'm writing down what I meant to write down. That we go M, that's the moment, times Y, it's this distance right there from the neutral axis divided by I. And by the way, sometimes they'll put a negative in there to try to, now if you have a negative moment, or if Y is negative, and then you would be able to figure out whether it's tension or compression. We're not doing that. We're going to observe the way that the moment creates either compression or tension. Same thing with the axial. Tension and compression, and in the next class we'll talk about what do they add or do they subtract. We'll combine the stresses together. So normal stress on the outside fiber, this is the main one that we will use, MC over I. Now also, keep this in mind, we'll use this a lot, but sometimes when we want to design something, what's nice is to combine C and I together into another variable that we call Z. And that Z is the section modulus. All right, thank you, Adobe, for trying to always improve my Acrobat reader. All right, so this is the section modulus. And it's equal to I divided by C. What's nice about that is if we go backwards and we know what the allowable stress is, and we know what the moment is that's applied to the thing, we could go to a catalog and pick out the section we want, the Z, the section modulus we want to pick. So when we're doing design, it's a nice, convenient way to check out and see what kind of section properties, how big the thing needs to be in order to meet our requirements, right? So just keep this MC over I, memorize that if you don't already have it memorized. And keep in mind, you could also replace it with M over Z when you want to work backwards. Now, that I got to think about what that is. We had that in statics, right? You found the centroid of things and parts, and then you about that centroid, often we would use something called the parallel axis theorem to be able to figure out. Well, maybe that's not the right way to say it. We would use the idea of the area moment of inertia, often called the second area moment of inertia, to be able to find the properties of that cross section. And it's resistance to bending. That's what that I is. And we talk about stress being the distribution of internal loads. Well, how are those internal loads distributed? I really determines for a particular cross-section how they're distributed and kind of describes it. More material to the outside of the thing, further away from the neutral axis, gives you a larger moment of inertia, and will help you distribute the stresses more throughout the entire cross section, and you'll have a smaller overall maximum stress because your I will be large. A large I gives you a smaller stress for a given moment. And it's really what the section properties work at. And it kind of tells you, the section properties, the moment of inertia, really gives you kind of a side, how is the material distributed? It turns out, like, you know, something that's material closer to the neutral axis doesn't do a whole lot. Stuff far away from the neutral axis does a lot more. That's why we have I-beams. The idea of an I-beam is really this. The middle part isn't really doing so much. This is called the web. These flanges, now this is not a symmetrical piece right here. But these stuff on the outside right here, it does a lot. And notice that the neutral axis kind of goes closer towards this larger flange. We call this the flange, right? Each of these is a flange, is a bigger flange than this one. So the neutral axis, it runs through the centroid, which we remember how to find that, right? That's like finding the kind of the center of area of the thing. And so these are all important things, right? And if we want to try to move, for whatever reason, the moment of inertia from a non-centroidal place to a different spot, right? From the centroid to a different spot, we use something called the parallel axis theorem, and we do a line over it for the moment of inertia, right? For the moment of inertia that goes through the centroid or the neutral axis. All right. So here I posted this up, and it's we could do a walk by walk. It's I think it's a good exercise for you to go through to look for it yourself. But to making a table to make a composite moment of inertia calculation is an important thing, and making it in Excel is something that you'll end up having to do quite often. I might make a separate video for this because I don't want to, it does take some time to go through, and I don't necessarily want to put through the thing. I think I did for the section modulus, I think I messed something up right here. For some reason, I need to fix this. Maybe I will remember to fix it right here, but that's not correct, right? What I'm writing right in there, and that's not correct. And so I'm sorry, I got down to there. But if I go through this process and find for region 1, right? There's region 1, and I find what the area is of this, right? It's like 5 by 1, and then I find the area of region 2, which is going to be based on the dimensions given right here. This is 10 inches right there, right? So this is going to be 10 times, this is thickness of 1 right there. So I get the area, and then 3 right there. I see that that's 10 times 1. I can see what the area of this piece is. I could see the location from a reference, which is going to be the bottom axis right here, of where the centroid is. I could just, from observation, see where the center is of each of these pieces from that, right? So 11.5 is where that is. 6 is where the center of that is from the bottom here. And then 0.5 is where the bottom is. And then I have AI times YI, right? So that times that equals this right here. This is the first area moment of inertia, and I do that for each of the pieces, 10 times 6 right here. So you can see this is a good thing to do in Excel because you just multiply that cell by that cell, you're golden, right? And then you sum them all up, and then you sum up the areas, and you divide this by this, and what we're going to find is we get the centroid, right? Or get the distance, and that's going to be this right here. That's going to be the C. In this case, we'll call that C min because this is the smaller distance. The C max is going to be the overall height minus the C min, right? So this is the further distance away from the neutral axis. This is the small one for this cross section. Now we want the moment of inertia. So you see right here, I've written the C max is right here. We want the moment of inertia. We take individual ones about their centroid, right? Individual centroids right here. And we get BH cubed over 12. That's a good one to remember. For a rectangle about its centroid is BH cubed over 12. In this case, the base is 5. The height, that's H, is cubed. That's 1 cubed divided by 12. Not a very big number. In this one, in this case, the base is this width right here, and the height is that right there, right? So it's going to be 1 times 10 cubed divided by 12. And that's a considerably larger number, but because it's harder to bend this guy about that axis right there, right? So you can think of this guy being bent about that axis, whereas this guy is trying to bend it about this axis, right? About the axis that's running right here, and it's hard to bend this right here. Easy to bend it this way, hard to bend it there. That's because that h gets cubed, right? BH cubed over 12. And then lastly, you can see that this is the width right here. This is the base, B, height cubed over 12. Also a pretty small number because, once again, it's kind of flimsy right there. But now we have parallel axis theorem, right? Remember the parallel axis theorem was written out as I, that's about the moment of inertia, or about, I should say, about the centroid, right? I said a moment of inertia. It's about the centroid, but you have to add in the area times the distance you need to move it to the centroid. Well, where is that right here? We need to move it for this piece. We need to move it from here to now like down to here, right? So this is the new location of the moment of inertia for this thing, so it needs to move. And we'll see that it needs to move 6.6, right? The idea here is that it was located at 11.5, and now it needs to move by 4.9. You could take my word for it. That ends up coming to 6.6, right? So it's the area times that distance it has to move from here to here, so this right here. That's going to be the 6.6 that it moves. And that's a big number. Look how much bigger that number is. It's much bigger than this. It's that distance that it has to move that's really causing it to have a lot of moment of inertia, right? It's resistance to bending. So you add those two together, because that's the parallel axis theorem right here, right? So that is the contribution of just this piece to the overall moment of inertia of the entire section. You do the same thing for this middle piece right here. We're going to move it from its center over to here. It's not as big of a movement to have to make. It's only about 1.1 does it have to move right here. You take my word for it, or we could go ahead and subtract out where the center of this thing is. I believe the center of it is the center of it is 6, but we needed to move it 4.9. That ends up being the 1.1. That's squared. So here its contribution due to it having to move. Relatively small because it doesn't moving very far. And we add them together. And so here is that plus that. We end up getting this. Lastly, we have this part right here. And it's going to move from its center, which is 0.5. It needs to move up 4.9. So that's 4.4 it has to move, right? Went from 4.9 is the location of the centroid of the whole thing together. This individual centroid is 0.5. The distance it has to move is 4.4. Square it times its area. That's a big amount. You add those two together, right? And so now we have these three, and now as soon as we have them all in the same, about the same axis, we can add them together. And that right there is the overall moment of inertia, right? So hopefully this seems familiar to you. It's something to go through and to get straight. And if we want to know the section modulus of this thing, there's two section moduli when you have a non-symmetric section, right? So this is not an I-beam. It's in like an offset I-beam, maybe you might want to call it. I don't know what you'd call it. I usually call this a built-up member, a composite member, maybe. But what you would do is you would take the moment of inertia about right here. So you go like 508.1 and divide it by the minimum, right? So this is a small right here. So this right here is going to be the section modulus for that side of the piece right there. And so that's going to be divided by 4.9, whereas the minimum one is going to be that 508.1 divided by this larger distance right here. All right, it's going to give you a smaller value, so 7.1. So we end up with 103.7 inches cubed. By the way, that's the section modulus units. And then this one is going to be 71.56 inches cubed. And in a table of these channels or of these pieces, you would find them. Now, I made this is very, very, very small. But you'll see, and not every book uses Z, by the way, but our book does. You can see that there's a Z right in there, right? So there's a Z, and by the way, this Z, because this is symmetric right here, it's going to be the same. There isn't two different ones. There's not a min and a max, but you can see that there's one about this axis, and then there's also one about this axis right there. So you can see that right there. We also have the radius of gyration is also another thing that's a shortcut that we might want to know. We use K in this book, and that's the square root of I divided by A. Right, that's a shorthand. So like if we're given the radius of gyration, what we do is we multiply a times k squared, gives us this. This is like a shorthand way of writing down, but it also can help us to evaluate the cross section to see how well is the area, the material being used. And then I think for my last one in this, because I'm actually attending a class. I guess I have 6 minutes left. I think I can do that in this time. Here is some a basic stress example, very, very basic, where we have from class 1. Do I want to do this? Yeah, I guess I have to. All right. So what we have here is we want to find out what are the stresses. Find all of the normal stresses at point A. That's point A onto this piece right here. So like right there is A. We want to find the normal stresses. So if we take a look at, here's our results from our statics. And we find, here's the axial. And we take a look at that, we see that it's pulling right there. This load right here has an axially pulling right there. So that is what we use for this. We say that's 1,500. And if we want the shortcut for or the equation to find for a circle is pi over 4 times the diameter. The diameter here is 1 pi over 4 diameter squared. We get this and we find that it's 1,910 psi. Pounds per square inch, right? This is pounds. This is inches squared, right? So we have pounds per square inch. The book will sometimes write it out this way right here. 1.91 K psi. But Dr. Deal learned it from some other book that likes to go KSI. So you'll see me go KSI all the time. It's a habit. I can't break it. I think it's more common than KPSI. They just mean 1,000 PSI, similar to kilonewtons and newtons. KSI is what I see almost everywhere else except for Shigley, right? Some books just like to do it their way. Now, for the stress at A, right there, we take a look at this and we can see that the one that's causing a bending stress at A is the 2,400 inch-pounds, right? The one that's happening about the y-axis right there, it doesn't do anything because that's actually about right here, that's going to be the neutral axis for that direction. But we do have one that's bending downwards. It's going this way right here. So it's trying to move these apart. So that's his tension, right? It's coming that way right here. That's why that stump is so important. So if we have the bending, it's going to be MC over I, right? And the shortcut for I, maybe I should have written that up above. I'll write it up above because it right here is going to be pi over 64 d fourthed. That is for a circle. That's a good thing to memorize. pi over 64 d fourthed, right? Some people use the radius, but we're usually given the diameter, so that's fine, right? And just something that you should note here is that now we could have m, and this is going to be d over 2 divided by pi over 64 d fourthed, right? So just note that one of the d's will cancel out right in there. So sometimes you will see this for a circle only of 32m pi d cubed, right? So don't worry about that for now, right? But just be aware. So this only applies for a circle, so we don't want to use it too often. Only when it's appropriate. Sometimes that's good for us. So we could find what the diameter needs to be if we want to go backwards. But so the bending stress that's taking place right here is going to be. I'm going to use this formula right here, and I'm going to calculate this out. When I put 1 inch in for here, I get 4.909 e minus 2 inches fourthed right there. So a moment that I'm going to use here is going to be the 2,400 times our 1 divided by 2. That's going to be c, right? 1/2. That right there, divided by my 4.909 e minus 2. And I end up with 24,450 psi, pounds per square inch. And I would write that 24.45 ksi, typically. And if we're going to put that on there, that would be the direction on this stress element that those two things are going to happen. And they're both, and by the way, they're in tension. So we want to make sure that we put in a tension next to them. We don't go positive and negative. We could think of compression as negative, but we generally are going to treat it that way. Now I got to go to class right now. I'm taking sitting through Dr. Slaybach's flight mechanics class. Here was another problem that I was going to run through and show that we could get the stresses. This is based on that example where we went through the thing and we wanted to find the maximum. Here is where the maximum bending moment was. And what we would do is find for that stress, the bending. And we might say it's the bending at A right here. We would say MC over I. You would find the I with the BH cubed over 12 right here. And plug that in. Of course, these were in millimeters right here, so I could have probably have done, would have been good to have done this. Maybe I'll do this anyway. So what we want to do is turn these into meters right here. So the base is 0.05. I'll be late to class. And 0.1 is the height cubed over 12. And you're going to end up with a very small number. So let's use, I like to use scientific notation because my calculator is like always in that anyway. Minus 6 m fourthed right there. So we have 2,460 Newton meters times our C, which is going to be 1/2 of the height, or 50 millimeters, or 0.05 meters, divided by our 4.167 E minus 6. And what we end up with, by the way, this is Newton meters times meters divided by meters fourth. So we get newtons per square meter. So when we end up with an answer of this, we get 2.952 e to the 7 Newton per meter squared. But the normal, I shouldn't say normal, not use it, the regular stress units that we use are pascals, right? Which is defined as a Newton per meter squared. And because we're almost always really, really big by over a million, we almost always use megapascals to report. So the answer is 29.52 megapascals. and it depends if the maximum bending, maximum and minimum, they're the same. It's at the same location, but we have to look at this and try to see what's happening. Like, okay, so if this thing is bending, if this is pushing down, it's going to be doing this right here, right? You could think of the shape. So at the top of the section here, right, because we know the maximum is here at A, so if it's pushing down like that, it must be compression on the top and tension on the bottom, right? So the maximum, if you're going to call tension positive and compression negative, the maximum is going to be 29.52 megapascals tension at the bottom at A, and the minimum is going to be 29.52 megapascals compression that's happening at the top of the section up here. So it's like well, actually it's any stress element along the top or any stress element along the bottom. That's what the answer is going to be. So it's tension and compression, and those are the things. So anyway, I'm going to go to class. This video was meant to try to refresh your memory about normal stresses and how to get them. So we will do shear stresses in the next video. And I bet this was way too long, but it'll be a little more succinct. Yes, 25 minutes long.